Hey, what's going on? So, I've already done two videos on this subject, but I just don't want to leave it at that. I'm curious to see, because at this point, we're really not completely sure what phenomenon is actually causing it to cool more quickly. Is it just basically getting a head start due to, you know, let's say the temperature of the liquid. And by the way, if you haven't seen this video yet, there's a part one and two that you should go watch first, else this might not make any sense. But um, let's say you have warm soda that's like 90 degrees from the trunk of your car, and then you wrap it with a paper towel, and then you wet it with, let's say, see, I don't know what cool tap water temperatures, I never measured it, but let's say it's 60 degrees. That's a 30-degree differential. So with the paper towel wrapped around it, it helps hold more water against the outside of the can. So even without putting it into the fridge, there's a temperature differential, and as with anything in nature, everything tries to balance itself. So the heat from inside the can is going to soak into the water on the outside of the can until they get to an equal temperature, until there's equilibrium. And that happens with everything. So I mean, if you, it's like taking two glasses of water, a hot one and a cold one. If you mix them, you're going to end up with the temperature that's kind of in the middle. So what I'm wondering is maybe until that equilibrium is hit, maybe all that does is gives the one with the paper towel around it a head start. Because instead of just being cooled by the cooler temperature inside the fridge, you have cool water touching the outside, which is basically liquid cooling. Liquid cooling is a lot more efficient than air cooling, and it's basically just sucking the heat out of there until the temperature of the soda on the inside finally equals the temperature of the water in the paper towel. So then it gets, like a 10-degree head start, and then at that point maybe it stays linear, and at that point maybe it would actually not cool any more quickly than a can that didn't have just a dry can without a paper towel or water. So meaning that for me to test it, what I could do is to get three sodas, one as a control, just a dry can, wrap two of them with a paper towel, one of them with the coolest water that my tap can possibly provide, and then the other one, drill a hole in the can first, measure the temperature of the liquid inside, and then get like my Thermapen or something, and then adjust my faucet until I get the water temperature to exactly what the until it gets exactly to what the temperature of the liquid on the inside is, and then soak the outside paper towel with that. That way, the liquid on the inside of the soda and the water around the outside of the soda are already at the same temperature. So that way, when we put all three in the fridge or freezer, if we want to do this more quickly, which I might do just to save time, because the last few times it's gone for a few hours, we should be able to tell that if my theory on the water is just soaking the heat out of it until they reach equilibrium, if that theory is correct or not, just by looking at the data. If that's not true, then they'll both cool about, they'll be, the lines for both the paper towel ones should be pretty much parallel with each other. Versus if there is something to that theory, then the one with the cooler water should actually pull ahead of the other one. But then what I wonder is if I lined them up. Well, but see, there really isn't a good way of telling when they reach equilibrium. But it makes me wonder that if they did reach equilibrium, if you line the starting temperatures together up at a certain point after they've already reached equilibrium, if they would stay parallel with each other, or maybe it's a combination of two things. Maybe the heat getting pulled out by the water helps it some, and then maybe also at the same time, even after they reach equilibrium, maybe the water helps act, as like a water to air or liquid to air kind of cooling system, and maybe it helps a little more. Maybe because the air conditioning or the air cooling process dries the air, sets up a really good situation for evaporation to happen. Maybe there's a little bit of evaporative cooling too. I don't know. There's lots of different things at play, but I think the next step in this would be to do three cans, two of them with a paper towel, one with really, really cool tap water in the coldest setting for my mixer tap, for just a faucet with one handle. Actually, I don't think mine's a mixer, but either way, the coldest water I can get out of my tap, and then I'll do one where I'll match the temperature of the water that I soak it with to the temperature of the soda inside the can. We'll put them all three in the fridge, and I might even use a fourth channel this time. I didn't do it the other times, but use a fourth channel just to measure the air inside of the refrigerator. That might give us a good idea of what's going on also, because we never actually had that. That was information that was missing from the last two videos that some of you might have been curious about. So I think I'm going to go do that now, and then I will report back with the results whenever it is done. So see you in a second. Alright, I am back with some awesome results. So the point of today's video, like I just said earlier, is to see if the temperature of the water that you soak the paper towel in gives it any advantage. Because if you think about it, let's say you have two metal cubes. One is super hot, one is super cold. You set them one on top of the other. What's going to happen? Well, heat's going to go from the hot one into the cold one until they basically reach equilibrium and they're both the same temperature. That's just how it works. So what I was thinking is that if you have a paper towel and you have really cold tap water, especially if it's in the winter and you live in the Midwest or something, and your tap water gets really cold down to like 40-some degrees, and your soda is in your pantry by your heater vent or your register, and it was maybe 80 degrees Fahrenheit, that's a 40-degree differential. So obviously as soon as you put that wet paper towel on there, that really cold 40-degree winter tap water is going to immediately start sucking heat out of the inside of that 80-degree can. And obviously that'll give you a huge advantage over the dry one, because liquid is a super good conductor, and it's really good at extracting heat. So it would give you an advantage. But obviously as soon as the temperature of the water on the outside of the can soaks up enough heat to where it basically is the same temperature as the can, then you no longer have that advantage, and then the curve at that point should be no different than the curve of a can with hot water on the outside instead of cool water. And so that's what this experiment was to prove. And as we can see right here, the red one was hot water, and it was 130-degree tap water, and the green one was 70-degree tap water. And as you can see, there is a difference, but it's okay. So the reason it seems like they started at different temperatures is because it transfers the heat so quickly that it's basically already reached equilibrium before I could even get the data logger started. So if you think about it, think of how much liquid and thermal mass a soda can has, and then think of how little thermal mass a single half sheet of paper towel soaked in water, but not super dripping wet, just lightly wet. There's almost no water in there at all, versus how much liquid is inside of an entire can of Coke. So obviously you wrap that around the can, and it's not going to take but maybe anywhere from 10 to 30 seconds for it to suck enough heat out to where it's already warmed up to whatever the temperature of the can is. And setting 3 cans up and trying to get the probes into the holes and trying to get them centered so they're not touching the edge of the can, and then getting the fridge closed, all that takes time. And so it could have been a minute or two that I had the door of the refrigerator open while I was trying to get this set up, and in that time obviously it already reached equilibrium, because I measured each can and they were all reading a little over 115 degrees before I put them in the refrigerator. And obviously they'd already cooled off before I even got it into the fridge, because over on the left side of the graph you can see that they're all reading under 115 at that point. So basically, if you look here, the hot water one started at 112. This one the cold one started at 110. So basically it gave us a 2-degree lead immediately. So, but as soon as the temperature of the water in the paper towel on the cool one heated up to the temperature of the can, because it sucked enough heat out to where it reached an equilibrium, at that point it stopped having an advantage, and the curves are basically perfectly parallel. So if we actually started these at the same temperature, like if I artificially shifted the data to where they are at the same time period, they would be almost perfectly on top of each other, as you can see. But that being said, there is a difference, which means that that is one of many other factors that are contributing to why this works. Obviously, if you use warmer water, then you're not going to get an advantage. But if you use cooler tap water that's cooler than the temperature of the can, then you will gain an initial little boost. And in fact, would be even better than that probably is just to run run your can underneath that cool water for, like a minute before you throw it in the freezer. But I guess that would be kind of a different story. But anyways, it was a success, I think, because that proves that it does give a tiny bit of an advantage. But obviously, this isn't this big of a difference between, the control and these. So obviously, there's still something else. If you look at this huge gap, it's still basically it takes twice as long, which tells me that there's something else going on here. So I'm gonna have to do some further experimenting, because I'm really curious what specific factors, what physics phenomenon are causing the ones that are wrapped in a wet paper towel to have such a big advantage. So there's two other things I think I could test that I can think of off the top of my head. One would be evaporation, but I don't know how I would test to see if evaporation is the cause of it. How would I prevent evaporation? That'd be the only way I can think of to test it. I guess you could artificially saturate the air with 100% relative humidity, but I don't know how to do that without building some elaborate rig. And even then, that'd be pretty tricky and probably not worth the time for something this stupid. So that I don't know how to do. But the other factor I think that's contributing to this is the fact that the paper towel is porous and has a texture to it, so it's actually adding surface area to. And while the paper by itself would probably act more of an insulator than a conductor, when it's wet, water's a really good conductor. So it's basically turning that extra surface area into a good heat sink, basically. So I think that does contribute. I just don't know how much it contributes, and so I'd like to get some results kind of like this, possibly tomorrow, to see if it's a surface area, and that'll be easy to test. All I would do is the same thing I did today, but instead of one hot, one cold, and one control, I'd still have a control, but instead of hot and cold, one of them will be cold water out of the tap with a paper towel, and one will be cold water out of the tap with loose leaf, like notebook paper. That way, we have something that'll still hold the moisture against the can evenly, but it won't really add any more surface area. It'll be a negligible amount. I know it increases the diameter technically, but it's by such a small amount, measured on the order of microns, that I don't think it'll be that big of a deal. So if there is a difference, it should be the surface area, and I don't expect it to be a huge difference. I think if anything, it'll be kind of like today's result, where it's, a couple of degrees, but it's big enough to see a difference. It's just not enough to make this giant gap up. So if anyone out there has any suggestions for what I could test to try to figure out what is going on here, let me know. Obviously, this is confirmed, but I don't want to just leave it at that. I'd actually personally like to know why there's such a big difference. So is it evaporation? Is it surface area? I don't know. Is it something to do with I don't know. There's so many factors that could be at play here, but we've tested a few of them, and so we kind of have an idea of what's going on, but there's some others that we still need to test. So if you have any suggestions on how I could easily test, if it requires a huge amount of work, obviously I don't think it's worth my time, but if you have any simple ones to test, like the kind of simple tests that I've been doing, let me know and I will give it a shot. But yeah, I will see you in the next video. Bye.